In the last video, we looked at a second derivative and we told concavity from it, but why? Let's suppose this is y is equal to f of x, my original function, and here's my derivative of it, okay? So here's my original function, here's the slopes of the tangent lines graphed out. All right, where we have concavity down, what's going on with the slopes of my tangent line? They're decreasing. The slopes of my tangent line are decreasing. I'm concave down here. Slopes of my tangent line are decreasing, right? Isn't this graph the slopes of my tangent line? Aren't they decreasing right there? How about right here? I have concave up, right? Concave up, the slopes of my tangent line are increasing. Concave up right here, slopes of my tangent line or my derivative, here's my derivative function, should be increasing. It sure is. So I would have something like this right here on that number line. Again, think of this as a graph of the slopes of the tangent lines, and this graph is decreasing there. So my slopes of my tangent line are decreasing here, and my graph is increasing there, so the slopes of my tangent line are increasing there, okay? So basically all we're doing with the concavity is we're looking at the first derivative as my original function, and we're finding out where my original function's increasing and decreasing. All right, let's look at our example now. Don't worry if you don't understand that right now, okay? It'll come. All right, use the graph of y is equal to f of x to find the signs of dy over dx and the second derivative of y with respect to x at the points a, b, and c. All right, so we have something like this. We have a graph that does like this, falls down there, and it does something like this, and that's y is equal to f of x, it says. Then it says, okay, here's a, here's b. It's a nice smooth curve, by the way. And it says, okay, here's c. Here's the x-axis, here's the y-axis. Now they want the signs of this stuff. The derivative with respect to x at x is equal to a, or dy over dx at x is equal to a. They want the same thing, dy over dx, x is equal to b, dy over dx at x is equal to c. All right, let's find out. Are these positive, negative, or what? Here is my original graph. Y is equal to f of x. This is the derivative at x is equal to a. So let's look at the slope of the tangent line at x is equal to a. Is it positive or is it negative? It's positive. So I'm going to say that one's positive. How about the derivative at x is equal to b? What is my slope of my tangent line at x is equal to b? Of positive or negative? Well, it's negative. How about at x is equal to c, my derivative? What is the slope of my tangent line at x is equal to c? It's going to be a positive as well, just like the first one. How about the second derivative of y with respect to x at x is equal to a, then at x is equal to b, and at x is equal to c? Let's see if those are going to be positive or negative. All right, second derivative at x is equal to a. So what are we going to look at here? We're going to look at a concavity. At x is equal to a, is this graph concave up or concave down? I'm going to say it's concave down, so that means my second derivative should be negative there. How about at x is equal to b? I'm looking at second derivative, so that means my concavity measurement should be negative there. How about at x is equal to c? How's my graph concave? Well, it's concave up there, right? So my second derivative at c should be a positive. All right, keep in mind what we had here. Y is equal to f of x. Keep that in mind, and we're going to work this second example. All right, so the second example, it looks a whole lot like this first one here, where we have an x-axis and we have a y-axis, x-axis and a y-axis. This time we're going to have a graph that looks something like this, looks like that, and looks like that. And notice what we're going to say here. Very, very, very important detail here. This is a graph of f prime. So this is the graph of the derivative function. We're going to say C is right here. We're going to say A is right here. And we're going to say B is right here. All right, so let's find the signs of my first derivative and the signs of my second derivative at those particular points, A, B, and C. All right, first derivative at x is equal to a. Careful. I'm not looking for the slope of my tangent line here. Why not? Because they're not giving me f of x. They're giving me f prime of x. So this is the derivative function. So what happens? What is this function at y, or at x is equal to a? What is this function? Is it positive? Is it above the x-axis? Or is it negative, below the x-axis? Well, it's obviously below. F prime, my derivative, is below the x-axis at x is equal to a. So that means my function is negative. Remember from algebra that if you're above the x-axis, you're positive. Below the x-axis, you're negative. How about at x is equal to b? What is this derivative function? It's up here above the x-axis, so it's positive. Now, what is this derivative function at x is equal to c? It's down here, so it's negative. Now, whenever I look at the second derivative here, what am I looking at? I'm looking at the derivative of this derivative, right? So I'm really looking at the slopes of the tangent line of this curve when I'm looking at second derivative here. So what is the slope of the tangent line today? It's positive. What is the slope of the tangent line at B? Negative. What is the slope of the tangent line at C? It is negative as well. Very, very important. You look at what they give you here because you treat it different if they give you f of x or f prime of x. All right, so let's go on to another example here.